So here is what I'm calling example number 3, and I'll start by drawing some axes for us to graph on. Okay, so the first thing I'm looking at here is I see a sine curve. Now, I see almost what I want. If I was to get rid of this 2 here, I'd see y equals sine x. I know exactly what that looks like. Starts at 0, goes to 1, back to 0, -1, 0. I'd have my curve written like that. But there's this 2 in front that's different. And what did we say that would change? Well, if it's not being done to the x, then that means it's going to affect the y value. And so for us, we're looking at how is that going to affect my y value, and what do we call that? The amplitude. Okay, so when I'm normally graphing this, I'm going up 1 and down 1 as my maximum and my minimum, but this time I'm going to go all the way up to 2 and -2 for my max and min. So when I go to graph this, nothing else is going to change. It's still going to be that same circle, but it's going to be twice as big. So now, starting at 0 for sine, I'll go, instead of to 1, I'll go to 2, back to 0, down to -2, and then back to my 0 to get all the way around 360 degrees. And there's my beautiful drawing of my sine curve with an amplitude of 2. From the x-axis here, you can see the maximum it went up was 2, and the minimum it went from the x-axis was -2. So that's why we say the amplitude is a distance, therefore it's always positive. If there's a negative in front, that's going to have another effect on it, which we'll talk about a little bit later. Okay? So go ahead and pause it and try part B if you're really up for it. If not, that one is a little bit different because it's not out in front. It's actually being done to the x, my angle. And so the first thing I would do is put parentheses around it so I know that that whole 1/3 x is my angle. And I'm going to have to take that and solve for all the values unless I memorize these. So go ahead and pause it, give it a try. All right, if you gave that a try, well done. If not, here we go. What is that going to affect? Well, since it's being done to the x value, then it's obviously going to have an effect on my x-axis. Now, how is that going to have an effect? Well, remember, our period of time that it normally would take a sine or a cosine curve to repeat itself would be 2 pi, 360 degrees all the way around. But as I mentioned before, because it's being multiplied, we're going to undo that by dividing by that 1/3. Now, normally we don't like dividing by a fraction. Instead, we always like to multiply by its reciprocal. So here comes that fancy 1 again of 3/1, or 3. Okay, so 3/3 is just 1. So when I multiply this original thing that I had by 1, it will not change the value of it. So the 3/3 cancels, and I just get a period of 6 pi. Now, don't forget, that is important. I know that that is where it's going to end. But what's even more important, in my opinion, is finding all those other points. Of course, we're going to start at 0, but what about those other ones? Well, remember, we said that we would find those by cutting it into fourths. So my quarters, I will find by taking this and just dividing it by 4. So my quarters would each be, if I simplified that, 3 pi over 2 in length. And I'm going to have to do that 4 times, like we've always done. 1 pi over 2, 2 pi over 2, 3 pi over 2, and so on. So this first one, though, is going to be 3 pi over 2. Then I'm going to have to add another 3 pi over 2, which if I added another 3 pi over 2, that would get me to 6 pi over 2, which would be 3 pi. And then if I did another 3 pi over 2 to that, I would get 9 pi over 2. And then another 3 pi over 2 would be 12 pi over 2, which is my 6 pi. So you can see I didn't change my graph at all. I just labeled it correctly, which I'm perfectly fine with. If you guys would like to do that as well, feel free to just label it correctly. It doesn't have to be drawn to scale. Because if you notice, 6 pi technically, if I was to draw this out correctly, would actually look like this. It would actually look like that, which if you notice is 3 times as big, which remember I told you this will have the opposite effect because they're x's, they want the opposite. And so when we're dealing with this, instead of just having our normal sine curve going 0, 1, 0, -1, 0, and looking like this, we're actually going to have them go by 3 pi over 2. And so it would then have the effect of still starting at 0, but then I'd have my 1 be here now at 3 pi over 2. And then my next one, which would go back to 0, would be at, we said, another 3 pi over 2, which is 6 pi over 2, or 3 pi. And then 9 pi over 2 would be down at -1. And then all the way back up to my 0 there. And so the actual graph of this, the effect it would have, it would be horizontally stretched to be 3 times as long. Now, I don't care that you guys take up a whole page of paper to write that many tick marks and find all that stuff, as long as you label my 5 key points and where those would be located at. Just like this, I'm perfectly fine with that. Okay, so go ahead and feel free to finish the graph of this. Hopefully you already got it. 0, 1, 0, -1, and back to 0 for my sine curve. And again, notice the amplitude did not change this time, still from 1 to -1, but my x-axis got horizontally stretched to be 3 times as large as it normally would have been for 2 pi. Okay, so feel free to label it correctly like I did up here and not stress about actually drawing it to scale and having this drawn out a big long sine curve. Okay, hopefully you got that. Let's try another one, but of course with cosine. All right, so in this fourth example, we're now dealing with cosine curves and a couple of different things. I haven't put too many yet, just one at a time. So what is going to be the effect on that normal cosine? If we were to get rid of this 3, you can see we just have cosine x. So what is that 3 going to affect? Well, it's being done to our what? Our angle, our x. And so that's going to affect our period, which is normally 2 pi. And remember, since it's being done to the x, it will have that opposite effect. Since it's being multiplied by 3, we will take our period and divide it by 3. And if that's our period, we can then use that to find our quarters and how long each of those will be, starting, of course, at 0 radians. So quarters, all I'd have to do is take that 2 pi over 3 and cut it into fourths. And since we're multiplying, we can do some canceling, 2 into each of those. And so my quarters would actually come out to be pi over 6. Which means all I have to do is increase by a pi over 6 to get my 5 key points, or my 4 quarters, on top of my starting place at 0. So I'll take 1 pi over 6, 2 pi over 6, 3 pi over 6, and 4 pi over 6. And of course, they're not going to want you to leave it like that. What are they going to want us to do with every single one of those? Simplify them. So this would be a pi over 3. This would be a pi over 2. This would be a 2 pi over 3. And that last point should always be what your period ends up at for now, because we haven't done any shifting yet. We'll get there, right? So now all I have to know is what does the cosine function start at and what does it go to for each one of those quadrantal angles. And remember, cosine is the complement to sine, and since sine starts at 0, we will start up at 1 for cosine. then it goes down to 0, -1, 0, and then back up to 1. And of course, this is not drawn to scale, but as long as you can label it correctly for those 5 key points, I'm confident that you'll be able to then evaluate and do anything else we need to with these. All right, go ahead and try part B. That one should be really easy to do now. Give you 30 seconds, give it a shot. All right, hopefully you gave that a shot. Pretty easy. The only thing that's changed from our cosine function was the 1/2. And since the 1/2 is not directly being done to the x, it's going to affect our y's in our y-axis. So as long as you know our original cosine would have started at 1, 0, -1, 0, and then back to 1. And this is what the original graph would look like. For what we call the parent graph, what we're trying to actually graph is this, which has that 1/2 in front, which is going to, like we mentioned, affect the y values. So instead of going up to 1 and down to -1, we're going to have an amplitude, we call it, of 1/2. So instead of starting at 1, we will crunch that down and take half of it. What about the 0? Take half of 0, you're still at 0. Half of -1, -1/2, 0, and 1/2. So you can see the effects of this is a vertical shrinking. All right, so just make sure when you're graphing this, you don't need both of them. If you want to draw another one right underneath it and draw that to 1/2 and -1/2, just like I said, make sure you label everything and it's all good. Because this is the only graph that I should see, and I don't want to see any V's or even U's. This is a cosine curve, a little bit different than a parabola and much different than 2 lines like an absolute value. All right, hopefully you're getting the hang of these. We will do more, so hang in there, but if you need to do more personally, then please do until you get it. So in this first section of graphing, I'm doing a little bit extra. I'm doing more examples than I might normally because this is very important, like I said, not only for just sine and cosine, but for 2 of the other trig functions that we'll get to in the next couple of videos. So hang in there. If you want to go ahead and pause it and try these on your own, by all means do. They're a little bit different, just little nuances here and there, and I wanted to give you one that also had a negative in front of the sign. All right, if you're able to come up with this first one, I'll be very, very impressed. Don't worry, I won't be able to tell if you did or not, but hopefully you can see what little nuances that this one does differ. And it's obviously, now it has 2 parts to that normal sine curve. So if you wanted to just start by drawing the original sine curve and then doing each of the individual things one at a time, that's fine. I will give you some pointers on which ones you should do first. But again, this one actually has more than just 2 things. We're going to have to do more than just the 2 and the 3. We're going to have to take care of this negative as well. So because this is being done to the x, it's going to affect our period. And this, since it's not being done to the x, is going to affect our amplitude. But this negative here is also going to have an effect on it. Because all these values that we would have gotten by evaluating sine, when we get those out, this is saying that we would have had to have multiplied them by a -3. And that negative is going to make everything the opposite. That's the word that we should use synonymously with that negative sign, okay, is the opposite. Because if I ask you for the opposite of 5, you would then write -5. Okay, so that's what that symbol means to us, is opposite. So how would this change our graph? What would this look like? So I'm going to draw it very lightly, which is hard to do with this iPad and pen, but I'm going to go with lighter colors so that you can see some of these things that would change. So the first thing I would draw is sine, which would be 0, 1, 0, -1, and 0. So this would be the original graph of just sine. Okay, now what we're going to do to that is change it up. And the few things that we could definitely change up is the amplitude first. The y values are easier than dealing with our x's. You know what I mean? So with this, we're going to have to take and rewrite an amplitude of 3. Okay, that's what our amplitude would be, is 3. But that negative is going to have the opposite effect, which then in turn means we're going to have what is called a reflection about the x-axis. So not only are we going to stretch this thing vertically to be 3 times as big, we're also going to take all the things that are positive and make them the opposite, reflect it about the x-axis. So all my y values that were positive are going to come down here and be negative, and all my negatives will be the opposite and come up here and be positive. So I will then take this and stretch it to be 3 and -3, but I'm going to rotate all of those. And so the zeros will stay zeros. The -3 will be what became from the positive, and then the 0 and the 0 over here will also stay, but this -3 will become the opposite and come up here to be +3. So you can see that it reflected. We rotated around that mirror, that reflection of the x-axis right here. Okay, so this one, which would have been up here at 3 times as big, flipped it down to the reflection over here, the other side of that mirror. Okay, and then this negative, which would have been down here from -1 to -3, will be the opposite, so it came up here to become +3. So I can now actually physically graph this to become my new form, which I'll go ahead and then delete what I had originally, and then all I got to do is make sure that I label it correctly. And so our period, we said, would also change. And our period was always, unless stated otherwise, for sine and cosine, 2 pi. But because they are being multiplied, that x is, by 2, we'll go ahead and take that and divide by 2, which actually works out pretty well because then those cancel out and we get our new period is just pi. But remember, we're going to then take that period of pi, and in order to find our quarters, we're going to take whatever our period is and divide it by 4, which there's no simplifying to do, so we're done. All we got to do is label it correctly. And so since our period was pi, we know that this should end here. But remember, from 0, we're going to go this 4 times. So I'm going to go 1 pi over 4, 2 pi over 4s, which if I go 2 pi over 4s, that would equate to pi over 2 when I simplify. And then 3 pi over 4s, and then 4 pi over 4s, which again, if I simplified that, I would just get pi. Okay, and there's the final product of my graph. If anybody got that, well done, very impressive. If you got this instead, you were really, really close. You just did not account for that negative sign. You would have had to have made all of this the opposite. Okay, so if you didn't try that one on your own, please pause it, try part B. See if you're getting this stuff, because I have one last example after this, and then we're done. All right, if you gave it a try, well done. Let's see if you got it right. First things first, I always look to see what I'm dealing with. In this case, I'm dealing with cosine, which I know is going to start at 1, go to 0, -1, 0, and then back to 1 to give this kind of shape. Okay? But we know that there's other things going on. 2 other things in this case, not 3 like the last one. We have an amplitude change, which remember, amplitude is always positive. It just tells us the length that we're going to go up and down from the x-axis. And then we also have something being done to our x, which is going to affect both our period and quarters. So when drawing this out, I know that my amplitude, I can go ahead and draw. I would have, instead of starting at 1 for cosine, I'd start at 2. Then I go to 0, then to -2, 0, and then +2. And technically, I can draw this, have my finished product, and then be done. But I want to make sure that I'm labeling everything I can. Now, that means I need the period and quarters. Remember, our period is always going to be 2 pi unless they say otherwise. And because this one is actually being multiplied, we're going to divide to undo it. Remember, x's want the opposite of us by that pi over 2 that it's being multiplied by. Now that's pretty nasty. So instead, we're going to go ahead and multiply by its reciprocal, which would be 2 over pi, so that all of this denominator cancels out to be a 1. So I'm left with 2 pi times 2 over pi, which it doesn't get much better than this problem right here, because that means we then know that the pi's, because everything's multiplying, will cancel out, and we just get a period of 4, which in turn means our quarters, we would just take that period and divide by 4 to get a length of 1. So just like here, we found our quarters were pi over 4, and we went 1 pi over 4, 2 pi over 4s, 3 pi over 4s, and 4 pi over 4s. We're simply going to go 1, 2, 3, and 4 for each one of those quarters to get those what would be quadrantal angles of the 1, 0, -1, 0, and 1. Okay? So hopefully you got that. Again, remember, I don't care if it's actually drawn to scale. For me, it's more important that you can do all of those other things. And if we needed to scale it, we were given a graph with the axes already labeled, then we hopefully would be able to figure out where each and every one of these things are. Because remember, we talked about many, many times, the power of radians is that we already know that this value right here is 3-ish. So we know it would be a little bit past right there if we are actually graphing that. All right, so here's the 6th and last example for us to go through. And what they're going to ask us to do is now work backwards. What if we were given the graph? Well, then they're going to want the equation this time, rather than what we've been always given was the equation, and we were asked to give them the graph. So in this case, they're going to first off start by asking us, well, which is it? Is it the cosine or is it the sine curve? And so you're going to have to first, just like you always did with the other ones, figure that out first so that you kind of knew the shape. And remember, the difference was one of them started at 0 and one of them started at 1. So which one would it be for starting at 0? Hopefully you said sine. So all we then have to do is figure out, is there something being multiplied by both the x and the y value? So is there any changes to our parent graph of just y equals sine x? Definitely, because it does not go up to 1, and it usually would just go to 2 pi with 1 cycle. You can see here that 1 period of time that it takes is actually just be pi. So we have to be able to work backwards here and tell me, first of all, what is the amplitude and what is the period or quarters? How did it change? So if you can look at the graph and say that, awesome. If you're already that advanced, if not, just practice until you get it, and you can always revert back to the formulas. Okay? Go ahead and pause it, see if you can fill those in. If not, I'll continue on with this last little explanation before we go and try it on our own. All right, now remember, the easiest thing is go alphabetically. Start with the A, all right? What is the amplitude in this thing? Well, you can see, like we talked about, it's not 1. It does not hit that high and low of 1. It actually looks like it's right at 1/2. So that would be what you should have gotten for that first part. And then a little bit more difficult is what would happen to get this whole cycle happening, this period of time for it to repeat right there, and then to do it again right there at 2 pi. Hopefully you can see that. We actually have it here in a length of pi, and then again all the way to 2 pi, even though they labeled that. Now remember, if you have just the 1, 2, 3 like we always have had when we were graphing as our tick marks, remember 2 pi is approximately 6.28, which is why it was a little bit past our graph of 6 there. Right? So if you're wondering why, or if you graph it on Desmos, things like that, check that out. You can play with these things very quickly to see how things will change around. It's really nice. Right? So the last thing we had to find was our period. And remember, we said our period was always 2 pi unless they say otherwise. And in this, we need to get a length of pi. So what would we have to divide by in order to just get pi? That would have had to have been a 2. And so therefore, we said to undo the dividing, we would multiply by 2. All right? The other way that you can do this is a little bit more algebraic in nature. You could say, you know what? I know my period is equal to 2 pi over b always. And if you wanted to solve for b, remember I told you, you have to have an equation with just one unknown. And if you want to solve for b, then you would need to know what p is. And we did find that the period of this thing was equal to pi. So now you could sit here and solve for b by multiplying it over to get it out of the denominator. And then you would have pi b equals 2 pi. And then you could go and divide lastly by pi to get b. Either way, you should have gotten this as your final answer, y equals 1/2 sine of 2x. So if you want to go and plug that into Desmos to see if you get this, by all means do. There's an app, or you can just go on the web and start playing around with it in all of these sine and cosine and see what happens when you change the amplitude, when you change that b for our period in quarters, and how it affects our graph. Throw in a negative here and there. Change it from sine to cosine, all right? Until you get this stuff, keep practicing. It's very important. We'll continue on with this in the next video and actually start taking them and shifting them up and down, left and right. Okay? So I put this background on here because I know this is how you're going to feel. All right? I know there's a lot of pressure with all these graphs, but with practice, it will become easier. Trust me. All right? That's all I got for you. It's been real fun. Take care.